Hola mundo! Welcome to Music Code, the show where we explore a topic in computer science, a topic in music, and combine them in creative ways. In this second episode, we're going to be looking at two basic building blocks, bits and semitones. Bits. What is a bit? It's a portmanteau of binary digit, and it's the basic unit of information for anything technological, such as a computer. Given that binary refers to anything with two components, it's no surprise that bits can take on two values, 0 and 1, true or false, yes or no, plus or minus. But how can we make computers do so much with only two values? Although a single bit can only represent two values, 0 and 1, 2 bits can represent 4 values, 0, 1, 2, 3. 3 bits can represent 8 values, 0, 1, 2, 3, 4, 5, 6, 7. What I've been showing you is what's known as the binary numeral system. In this system, each position n takes on the value 2 to the power of n. So if you want to know what value a binary string represents, you simply look at all the positions with 1s in them, look at the value that corresponds to it, and then add them all up. Notice that I also started counting at 0 instead of 1. This is very common in computer science, and it's known as zero-based numbering. More generally, a sequence of bits is known as a bit string, and it can represent more than just numbers. It encodes basically anything needed by the computer. Numbers, letters, images, funny cat videos, video games, and even AI. We call a bit string of 8 bits a byte, not spelled B-I-T-E, but spelled B-Y-T-E, to differentiate it from bit, which is spelled B-I-T. I actually don't know why they decided to call it byte, but anyway. 1,000 bytes is a kilobyte, 1 million bytes is a megabyte, and 1 trillion bytes is a terabyte. You may be familiar with these terms as you may have encountered them when you were running out of disk space to store all those funny cat videos. But bits and bytes do more than just store static information such as images. They encode instructions that tell the computer how to do its magic. For example, how do you think the phone or computer that you're using to watch this video knows how to display this video to you? Well, it's going through a bunch of bytes in memory that tell it how to display this video on your screen. Now you may be saying, hold on. I have a friend who's a computer scientist, and she most certainly does not write code in binary. And you're right, we most certainly don't write our code in binary. As I mentioned in my previous video, we write code in higher level languages such as C++ and Python, which is a lot easier to understand than a bunch of ones and zeros. This higher level code then gets compiled by a compiler which is itself written in machine language into a lower level language such as assembly, which is represented by a bunch of ones and zeros. And this is the language that computers know and understand to run your code. Let's take an example to make things a bit more concrete. This bit of C++ code takes a number and returns that number multiplied by 2. Now, even if you're not familiar with programming language, you can kind of understand what's going on, because we're using words such as number, twice, and return. A C++ compiler would then take this code and convert it into assembly language, which is a lot harder to understand even for computer scientists. But this is the language that machines understand, and it's represented as a series of ones and zeros. So the next time you interact with anything technological, which I guess you're doing now, just remember that underneath it all, it's just a bunch of ones and zeros. And with that, let's move on to a different type of building block. Semitones. Remember how in the last episode we saw that in Western music, we have 12 distinct pitches arranged into octaves? The smallest distance between any two distinct notes is a semitone. In other words, they're just the notes adjacent to each other on a piano, a guitar, a viola, or just about any other instrument. Semitones are sometimes called halftones, which suggests that there's something called a full tone, or just a tone. And there is. A tone is just made up of 2 semitones. With semitones and tones, we can build lots of musical things. For instance, remember perfect fifths from the last episode? Well, that's just a nicer way of saying 2 notes that are 7 semitones apart. In fact, all intervals, if you're familiar with them, are just 2 notes separated by differing numbers of semitones. A minor second is 1 semitone. A major second is 2 semitones, or a tone. A fourth is 5 semitones. And of course, an octave is 12 semitones. What about scales? Scales, which we'll cover in a bit more depth in a future episode, is just a series of notes arranged by pitch. The most commonly used scales are heptatonic scales, which is just a fancy way of saying scales with 7 notes. And we can describe these heptatonic scales with semitones and tones. The major scale can be described as tone, tone, semitone, tone, 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 semitone. The natural minor scale can be described as tone, semitone, tone, tone, semitone, tone, tone. But we don't have to limit ourselves to just 7-note scales. Here are a few non-heptatonic scales that I like a lot and I use quite a lot. The half-whole diminished scale is a scale that has 8 notes, and it's described by semitone, tone, semitone, tone, semitone, tone, semitone, tone. The whole half-diminished scale is similar, but it starts with a tone. Tone, semitone, tone, semitone, tone, semitone, tone, semitone. The whole tone scale has only 6 notes, and it's described by tone, 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 tone. And the chromatic scale is defined only by 12 semitones. Semitone, 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 semitone. Most of the music we hear is actually built upon scales. Chords, for example, are built using specific notes in a scale. The most common type of chord is a triad, which, to put it in imprecise terms, are 3 notes that are near but not too near to each other. To put it in COVID terms, these are 3 notes that are hanging out but at a safe social distance. To put it a bit more precisely, a triad stacks the 1st, 3rd, and 5th positions in a scale and plays them together. The scales we just looked at actually give us the 4 main triads. The major scale gives us the major triad. The natural minor scale gives us the minor triad. The half-whole diminished scale gives us the diminished triad. The whole half-diminished scale gives us the same diminished triad. The whole tone scale gives us the augmented triad. Although not a typical triad, the chromatic scale gives us a cluster triad. Now for this last segment, where I combine the 2 topics I just presented, let's come back to our scales. Semitones and tones are a lot of letters, aren't they? What if we represented them instead by 0 for semitone and 1 for tone? Well, now we have a binary string, and we know how to convert from a binary string to numbers. So this means that the major scale is represented by the binary string 1101110, which is equivalent to the decimal number 110. The natural minor scale is represented by the binary string 101111, which is equivalent to the decimal number 91. The half-whole diminished scale is represented by the binary string 01010101, which is equivalent to the decimal number 85. But remember, we can also take any number and convert it back to its binary string. So this means we can take any number and make a scale out of it. Obviously, not all of these scales will work well, and some of them will be really long. Also note that any binary string is equivalent to the same string with as many leading zeros as you want, which is problematic in our case given that zeros represent semitones. What I'll do is focus on binary strings of length at most 12. So I'll sample a number randomly between 0 and 4096, which is 2 to the 12, convert it to its binary representation, and then I'm going to read the binary digits from right to left. Recall that a 1 represents a tone and a 0 represents a semitone. And so I'm going to construct the scale in this way until I reach an octave, and this will be my scale. Here are some examples. So the root of the scale I'll select by playing in the lower octave of my piano. My software will create triads built on whatever scale was sampled, and start jiggling them around the piano. And so these jiggling triads will start dropping particles onto the lower piano, which is where I'll do my improvisation. If I hit notes that are in the scale that was sampled, then these will lift the keys and it'll start moving the little particles around, and it'll create an interesting visual. Enjoy.